In the previous class, we started talking about trusses, and to find out member forces in trusses, we used method of joins, and we also solved some problems. So this one was our tutorial sheet 2, which we have already dealt with, and I think we have also solved the problem number 1 in tutorial sheet 3. So today I will discuss question number 3 and 4. In question number 2, you can see that calculate the support reactions and internal force. Yeah. Question number 2 can be solved using method of joins, which you already know, and we have already solved a couple of problems, couple or even more problems using method of joins, and you can do that. Do this problem yourself. So today we will talk about a new technique called method of sections, which are useful in certain type of situation. And we will use that technique to solve question number 3 and 4. So the method we are going to use here is called method of sections. So how is method of joins different from method of sections, and what is our intention here? So just like the case of method of joins, we are trying to find out member forces in truss members. Let's say, for example, you have this structure. All dimensions are given. An external force of 1000 Newton is being applied on the joint A, and now you can use method of sections, method of joins, which you already know, to calculate any member forces. Let's say the question is to calculate member forces in let's say GC or BC or GF. In that case, what do you need to do? You first need to take the structure as a whole, draw the free body diagram, calculate the support reactions. After that, you solve joint by joint, first joint, second joint, etc. You solve as much joints as possible to calculate the required member force and see whether it is in tension or compression, which will be represented by its direction, which its sign. Okay. Now in the case of method of sections, we want to the ideas are essentially same, but here we will use a shortcut to find out member forces in specific member or members. For example, in this case, let's say you would like to find member force in GF. So that's not going to be easy, right? You take the whole structure and find out the support reactions, solve this joint, then solve this joint, because here again you have 3 unknowns, and this joint, after that you can solve this joint, find out GF. So that is going to be time consuming. So if a whole structure is in equilibrium, each part of the structure should also be in equilibrium. If we section the structure in such a way that we also consider the internal forces where we section. So the idea here is that earlier we used to consider equilibrium of each joint. Now we will consider equilibrium of part of a structure. So however you section it, each part of the structure should be in equilibrium, because the whole structure is in equilibrium. So here in this case, if you would like to find out member force in GF, we will use this AA section. We will cut the structure here and consider the equilibrium, force equilibrium of the part on the left. So if we do so, it's possible to calculate member force in GF straightforward in one step. So here, if we cut it here, and why are we cutting it here? Because we want to find member force in GF. So we cut in such a way that the cut pass through GF and cut pass through minimum number of members. So when you cut, don't cut through the joints. Cutting through the joints will make it very complicated, and it's not suitable for a solution. So we will cut through the members and not through the joints, and cut should pass through the unknown, and cut should ideally pass through minimum number of members, and that may not be the case usually if you have multiple. That may not be the case in all problems. If you are being asked to calculate 2 or 3 specific members, and there may be another choice of section which will be suitable for you to take. So there is no predefined technique using which you select the section. You use your intuition and logic to select a structure, to select a section, to calculate the unknowns. Here let's say you have taken the section this way. Now how does that help us? So we have okay, right, so it's cut here. Now you have A, B, C, not C, G, and this is GF, right? Here you add F, here you had C, okay, here you have F. Now of course you have your external force here. Now since the whole structure is in equilibrium, this part should also be in equilibrium, but since we have made the cut here, we also need to consider the internal force in these members. So internal force in this structure, but when you cut it, this becomes an external force on this part. Okay, BC, member force BC was an internal force here for the whole structure, but since we have cut it and since we are considering only this portion, the member force in BC becomes an external force. And we will like we usually do, we will simply assume that it's tensile, so it should be away from the joint. So here you have another external force, here you have another external force, which is basically internal force for this structure. So we will call this one FGF, FGC and FBC. Now I told you that using this technique we can calculate the member force in GF in one step. How do we do that? Now how many unknowns are here? How many unknowns? many unknowns do we have here? GF, GC and BC. 3 unknowns. And how many equations? Net force in x direction should be 0, net force in y direction should be 0, net moment about any point should be 0. So 3 equations and 3 unknowns. So definitely we can solve it. So what I promised you was correct. You can solve it. You don't need to solve first this joint and this joint. You don't need to go like that. You can actually use a single step. So 3 questions and 3 unknowns. So you can use the conventional method to find out to solve GF here. But let me say, maybe in this problem there is actually a much easier. We can further simplify the procedure. How do we do that? So that's something. Always look at the unknowns. 1000 Newton known force, 1, 2, 3. These 3 are the unknown forces. What are the line of action of unknown forces? This is the line of action of GC. This is the line of action. These are line of actions. Okay, this is the line of action of. It's an infinite line. Okay, line of action of BC. This is the line of action of GC, and this is the line of action of GF. So 1, 2, 3. These are the 3 lines of actions of unknown forces. And what does moment equilibrium say? Moment equilibrium say if you take moment about any point, the sum should be 0. And what is the definition of moment? Force multiplied by the perpendicular distance. To be more specific, if you are taking a moment about a point, force multiplied by distance between line of action of force and the point. So if we choose a point in such a way that many unknowns are passing through that point, then that unknowns will not be present in the equation. Listen carefully again. If we choose the point about to which we take moment in such a way that that point has as many unknowns are possible passing through it. Okay, if you take moment about this point, you have to multiply all these known and unknown forces. Known force is not a problem. It's already known. We know the value, so we don't need to worry about it. So we have to multiply member force BC with this distance, member force GC with this distance, and member force GF with this distance, and add them up. So you have 3 unknowns in the equation. So if you choose B, what is the distance between line of action of BC and point B? 0. It's gone. But you still have 2 unknowns remaining. If you choose G, both GF and GC are passing through this point. So those forces will not be there in the equation, because perpendicular distance between line of action of these forces and this point is 0. So the only unknown remaining will be BC, right? Wonderful. So you will get member force BC in one step. BC will be the only unknown in the equation. But in the question you are not being asked to calculate BC, you are being asked to calculate GF. So we would like to find out a point in such a way that all other unknowns disappear and GF appears in the equation. So we want to calculate GF, so we will not choose a point on GF, because if we choose a point on GF, GF will not be there in the equation and we will not be able to solve GF in a single step. So what are the other 2 unknowns? What are the lines of actions of other 2 unknowns? That is this one, this is the one line of action, and this is one line of action. And where are they meeting? They are meeting here. So if you take moment about this point, line of action of BC and line of action of GC are passing through this point, and those member forces will disappear from the equation and only GF will remain. So that will make sure that GF is the only unknown in the equation and you can calculate GF in a single step, right? So that's the easiest way to deal with the problem. So first we looked at a method of joins. We found out that it was very difficult. You have to do many steps. Then we found out the section here and used the method of sections, and we still had to use 3 equations and 3 unknowns. But we figured out that if we take the moment equation in such a way that many unknowns are passing through that point and the unknown which we need to calculate is not passing through that point, then at that point, using that point, we will be able to calculate the required unknown easily. So that's the idea here. And one thing to note here is that when you are taking moment about any point means any point. You can take moment about any internal points in the structure, inside the structure, outside the structure, at at a distance far from the structure, wherever. So this point about which I am taking moment is outside the structure, but that doesn't matter because moment about any point will be 0 if the system is in equilibrium. So if I take moment about C, net moment about C should be 0. So member force BC multiplied by 0, member force GC multiplied by 0 gone, and member force at A, this is the another force. So what is the line of action of this force? Line of action of this force is this long infinite line. This is the line of action. So what is the distance between line of action of this force and this point? Line of action of this force and this point, 2 plus 2, 4. So 1000 multiplied by 4. Now about this point, this is tending to rotate the structure in which direction? About this is tending to rotate. This is the line of action, right? So this is about this point, it's trying to rotate in this direction. So that is anti-clockwise direction, means we'll take it positive. Now this gone, now only remaining force is this one, GF. So FGF multiplied by, what is the distance? This is the line of action of GF and this is C. What is the distance between line of action of GF and C? C and line of action of GF. So that distance is 2 meter, right? Now this is the direction, and about that point C, you can see that this is the line of action. So it's tending to rotate the structure about this point about which you are taking moment in, again in anti-clockwise direction. Again you have positive sign. That's it. Other two forces are not present in the equation. Sum is 0. So FGF into 2 is equal to minus 4000 and FGF is equal to 4000 by 2 minus 2000 Newton. See, answer very easily. For such a difficult problem, we have found out the answer very easily. Okay. So like I told you, we will choose for if the question in the question if you are being asked to calculate BC, you would have chosen this point because these two forces will be gone. But if you were being asked to calculate GC, then there is no common point through which BC and GF are passing. So in that case, you will probably need multiple equation. You can use one moment equation and one force equilibrium may not be, I don't know, we have to check that. No, in that case we have to take in this direction. So if you are being asked to calculate GC, you will not get answer in a single step. You will have to do multiple steps. So this is the basic idea here. Okay. Yeah, so one more thing here, we got negative value for FGF. We assume that we have tensile force in GF, right? The forces are away from the junction because we assumed it to be tensile, so our assumption was wrong. We have compressive force. We have compressive force in FGF, so that's okay. So I'll give you I'll try to give you some help for question 3 and question 4, and you have to do it yourself. So this is question number 3. Here what is the question? Use method of sections to determine the forces in member BC, CF and FE. State if the members are in tension or compression. Oh, this is not difficult, right? You have to find out member force in BC, CF and FE. So how will you take section? You will take section in such a way that you have unknown member forces in your equilibrium equations. So we will cut through the members which we want to calculate, and we will consider the equilibrium of the right hand side. So here will you use the technique I have told you here, choosing this particular moment? Actually that's not necessary here, because anyway you have to find out member force in this member and this member. You have to calculate 3 unknowns, and you will have 3 equations for the right hand side. So you have to use 3 equations, and you have to use the 3 equation system, algebraic system, linear algebraic system. So if we cut it here, we have E, C and D. C and D. Assume that we have tensile force in each of these cut members, so forces will be away from the joint, and EF, you had F here, so we'll call it FE. This is FC, and this is BC. you have unknown force 600 pound here and 800 pound here. So you can convert pound to Newton if you like, or it's not necessary here. You can use pound, but you will get the answers also in pound. That is, these are pound force. Okay, that is the only difference. So here, how many unknowns do we have? 1, 2, 3. 3 unknowns. And how many equations do we have? 3 equations. So unknowns are FFE, FFC and FBC. 3 unknowns and 3 equations. Which are 3 equations? Sigma fx is equal to 0, sigma fy is equal to 0, and net moment about any point should be 0. Now here you will need these angles to make to write down the equations. So this is 4 and this is also 4, tan inverse 4 by 4. So this angle theta, what will be theta? Theta will be equal to tan theta is equal to 4 by 4. So tan inverse 4 by 4, that will be 45 degree. So this is 45 degree. So equation number 1 will be net force in x direction 0. So that will be, so these two are completely vertical, so we don't need to consider. We have a minus FFE, which is towards left, so we have, I've taken negative, and we have FBC. FBC is also towards left, I've taken its negative, and we have FFC. FFC cos 45, that is also FFC cos 45 is the horizontal component of FC, and it's also negative because it's also acting towards left. Sum should be 0. Net force in y direction should be 0. That means that so FFE and FBC are fully horizontal, so they are not there in y direction. Minus 600 is downwards, it should be negative. Minus 800 is again downwards, so negative. And FFC is FC sin 45 will be the component of FFC in vertical direction, and that is upward, so it is positive, which is equal to 0. Now we still have 3 unknowns and 2 equations only. We need moment equation. We'll take moment about which point? Any point. You can take moment about any point, but I'll just choose C to avoid a long equation. So because FFC and FBC are passing through C, so I'll just take moment about C. You can also take moment about F. These two will be gone. That is also fine. So I'm just taking moment about C. So if I take moment about C, I have FFE, what is the perpendicular distance between line of action of FFE and C? This is the line of action of FFE, right? This horizontal line. What is the distance between line of action of C and FFE? That's 4 feet. I'll go. What is the sign of it? So about this point, about C, FFE is in this direction, so it's tending to rotate the structure about, this is the point about which we are taking moment, so it is tending to rotate in anti-clockwise direction. So anti-clockwise means positive. And next you have 800 pound force. What is the line of action of 800 pound force? This is the line of action. This long line is the line of action. What is the distance between line of action of 800 pound and point C, that is again 4 feet, so 4, and it is tending to about C. It's acting in this direction, so it is tending to rotate the structure in clockwise direction, so negative sign equal to 0. So you will get FFE directly from this equation, FFE and FC directly from this equation. Substituted here and you will get FBC. Easy and straightforward. So only thing you need to consider here is the only place where you are likely to make mistake is the moment equation. Please make sure that you know how to calculate moment of any force. Remember, force multiplied by distance between line of action of force and the point about which you are taking moment. You need to make sure that you understand this idea. So that's it with problem 3, and let's go to problem 4. Now the last question. Determine the forces in members DC, HI and JI of the truss. If the members are in tension or compression, state if the members are in tension or compression, and there is a suggestion here. So you have to calculate DC, HI and JI. DC, HI and JI. So these DC, HI and JI. So those are the 3 members you need to calculate. So if you make a cut here, single cut here, TT, then there are 4 unknowns. In the upper part there are 4 unknowns, right? 1, 2, 3, 4. 4 unknowns, but we have only 3 equations, 3 equilibrium equations. So 4 unknowns and 3 equations you can't be solved in a single step. You need additional equations. So that's why we are taking an extra section. So the extra section should be made in such a way that our unknown should be involved in it. So the second section SS is cutting HI and DC, which we need. In addition to that, it is cutting extra 2 members. So in the section TT, we have 4 unknowns, 3 equations. In section SS, we have 1, 2, 3, 4 unknowns and 3 equations. But out of these unknowns, some are common. So number of unknowns will count. Number of unknowns for TT, you have HI, IJ, HI, IJ, JC and DC. JC, DC. And for SS you have HI, which is already here, JH, JD and DC. DC is already here. So total number of unknown 1, 2, 3, 4, 5, 6. 6 unknowns. And how many equations? From first section 3 equation. From second section 3 equation. So 3 plus 3, 6 equations. So 6 unknowns and 6 equations. You can solve the system. So this is the in the first from from the first section you have £1,200 here, 1,600 pound here. Any other unknowns? No. And this is F. Oh, I forgot F H I N C H I. This one is F J I, and this one is F J C, and this one is F D C. So 4 unknowns here. Sigma fx is equal to 0, sigma fy is equal to 0 here. So all these dimensions are given, so you can find out the so all these so what will be this angle here? This is 6 feet and this is 6 feet, so this will be 45, and this is correct, 6 feet, 6 feet, 6 feet, 6 feet. This is also 45. All others are either horizontal or vertical, so no issue. And you can take moment about let's say arbitrary, this point about D, you can take moment if you want. So you have 3 equations there, and I don't think I can erase this. Okay, what to do? So that was a bad idea. I'll draw it, no issue. So you have next case, you have so this is the, you can see this is the S section. So you have H I here, so this is F H I, and this is F H J, and this is F J D, and this is F D C. So unknowns. Here you have 1,200 pound. Here you have 1,600 pound. I think that's it. Now from here again, compare it with this system. These are the 4 unknowns here. Now these are the 4 unknowns. So 2 unknowns are common, HI and DC are common. FHI and FDC are common, and these two are extra unknowns. So total 6 unknowns. Here also you can write down net force in x direction 0. Now that is very simple. There are, how many forces are there in x direction? You have FHJ minus FJD, right? FHJ towards right and FJD towards left, equal to 0. Net force in y direction is equal to 0. So so minus 1200, minus 1600, downwards, right? Everything downwards. Minus FHI minus FDC equal to 0. And net moment about let's say this point D, net moment about D is equal to 0. So what will be that? Line of action of JD is passing through D, line of action of HJ is passing through D, line of action of 1600 Newton, that is 1600 multiplied by line of action. What is the distance between line of action of 1600 and D? This is the line of action of 1600. Distance between line of action of 1600 and D is 9. So that tends to rotate the system in clockwise direction, so negative. Now take DC. DC is passing through D, so perpendicular distance between line of action of DC and D is 0, gone. HI, FHI. What is the distance between line of action of HI and point D? That is 6 plus 6, 12, and it is tending to rotate the system in what direction? Anti-clockwise direction, so positive. Now you have 1200 pound force. So this is the line of action of 1200 pound force. What is the distance between line of action of 1200 force and point D? 6 plus 6 plus 9, so that is 21. So 1200 into 21, is it positive or negative? It is tending to rotate the system in anti-clockwise direction, so that is positive, equal to 0. 3 equations. Similarly here also 3 equations. Here you need to consider this angle, which is 45, and you have to take the components of JI and JC into horizontal and vertical direction. So that will not be very difficult. So you have 3 equations here and 3 equations there, and that makes a total of 6 equations and 6 unknowns. So you can solve for all members asked in the question, and you can state that if the member force is positive, you will state that your initial assumption was correct and member force is actually tensile. And if member force turns out to be negative, you will state that your initial assumption was wrong and member force is actually compressive. So that's it. That's how you solve the problem. So with that we conclude this section.